Fill a glass with water, drop in an ice cube, and something happens that you've seen so many times you've probably stopped questioning it entirely. The ice floats. It just sits there on the surface, bobbing gently, completely unbothered by gravity in a way that seems almost rude toward the laws of physics. And here's the thing that should actually stop you. This is bizarre. Genuinely, scientifically bizarre. Because for almost every other substance in the known universe, the solid form is denser than the liquid form, which means the solid version sinks. Water is one of the only common substances on Earth that breaks this rule, and if it didn't break it, the consequences would be so severe that complex life on this planet might not exist at all. So why does water do this? The answer involves the strange geometry of a single molecule, a phenomenon most people have never heard of called hydrogen bonding, and a planet that owes its entire habitability to a rule-breaking exception in basic chemistry. Let's start with the general rule water is violating, because understanding the exception requires understanding what's normal first. In most substances, when you cool a liquid down into a solid, the molecules slow down and pack themselves closer together. Think of it like a crowded room where everyone stops moving around and just settles into the tightest possible arrangement. Tighter packing means more mass squeezed into a smaller space, and more mass in a smaller space means higher density. Higher density means the solid sinks in its own liquid, every time, in virtually every substance you can think of. Molten wax sinks below liquid wax. Molten metal sinks below liquid metal. This is the standard, expected behavior of matter transitioning from liquid to solid. Water does the opposite, and to understand why, you need to actually look at the shape of a single water molecule, because that shape is doing almost all the work here. A water molecule is made of one oxygen atom bonded to two hydrogen atoms, and crucially, those two hydrogen atoms aren't positioned on opposite sides of the oxygen in a straight line. They're bent at an angle of roughly 104.5 degrees, giving the whole molecule a shape that's often compared to a wide, shallow V, or sometimes to a Mickey Mouse silhouette if you're picturing the oxygen as the head and the two hydrogens as the ears. This bent shape isn't a minor detail. It's the entire reason ice behaves the way it does. Now here's where hydrogen bonding comes in. And this is genuinely one of the more elegant pieces of basic chemistry once you see how it works. The oxygen atom in a water molecule pulls electrons toward itself more strongly than the hydrogen atoms do, which gives the oxygen side of the molecule a slightly negative charge and the hydrogen side a slightly positive charge. Water molecules are essentially tiny magnets, with a negative end and a positive end. And because opposite charges attract, the slightly positive hydrogen side of one water molecule gets pulled toward the slightly negative oxygen side of a neighboring water molecule. This attraction is called a hydrogen bond, and while it's weaker than the bonds holding individual water molecules together internally, it's strong enough to meaningfully organize how water molecules arrange themselves around each other. In liquid water, these hydrogen bonds are constantly forming and breaking and reforming in a chaotic, fast-moving dance, allowing the molecules to slip and slide past each other and pack together relatively closely, similar to how people can squeeze into a crowded subway car if everyone's constantly shifting position. But when water freezes, everything slows down dramatically, and those hydrogen bonds stop breaking and reforming randomly. Instead, they lock into a fixed, stable, repeating pattern. And here's the critical part. Because of that bent, V-shaped geometry of each individual water molecule, the most stable arrangement those hydrogen bonds can form isn't a tightly packed cluster. It's an open, hexagonal, lattice-like structure, almost like a three-dimensional honeycomb, where each water molecule bonds with four neighboring molecules in a very specific, spread-out geometric pattern. This crystalline lattice, which is literally what ice is at the molecular level, actually holds the water molecules farther apart from each other than they were able to get away with as a chaotic, freely moving liquid. This is the counterintuitive core of the entire phenomenon. Freezing water doesn't pack the molecules tighter together the way freezing almost everything else does. It forces them into a more spread out, structured arrangement, specifically because that bent molecular shape and the hydrogen bonding pattern it creates only stabilizes properly in this open lattice formation. More space between molecules means less mass packed into the same volume, which means lower density. And ice, being roughly 9% less dense than liquid water, floats. For the exact same reason a piece of wood floats on water. It's less dense than the liquid it's sitting in. So what would actually happen if water followed the normal rule instead? If ice sank the way essentially every other frozen substance sinks below its liquid form? The consequences would completely reshape the planet, starting with something most people never think about: how lakes, rivers, and oceans freeze from the surface downward rather than from the bottom upward. Right now, when a lake gets cold enough, ice forms on the top surface first and floats there, acting as an insulating layer that actually helps protect the liquid water underneath from losing additional heat to the freezing air above. Fish, aquatic plants, and countless other organisms survive winter specifically because that floating ice cap exists between them and the brutal cold outside. If ice sank instead of floating, newly formed ice at the surface would immediately drop to the bottom of the lake or ocean, exposing a fresh layer of liquid water to the cold air, which would then freeze and sink as well, over and over, in a continuous cycle. Bodies of water in cold climates wouldn't freeze from the top down with a protective cap. They'd freeze from the bottom up, solid, potentially all the way through, especially in shallower or more consistently cold environments. Entire aquatic ecosystems that depend on liquid water persisting beneath a frozen surface simply wouldn't be able to survive winter under those conditions. This has implications that stretch far beyond individual lakes, too. Ocean currents, global climate regulation, and the long-term thermal stability of the entire planet are deeply influenced by how water behaves at temperature extremes, and many scientists studying the origins of life consider this density anomaly a genuinely significant factor in why liquid water was able to persist reliably enough, in enough places, for long enough to support the development of complex life in the first place. It's one of several so-called fortunate properties of water that make it uniquely suited among common substances to sustain biology as we understand it. What makes this whole phenomenon even more remarkable is how specific the cause actually is. This isn't some broad, mysterious property of matter in general. It comes down to one single geometric detail: the bent, roughly 104.5-degree angle between the two hydrogen atoms in an individual water molecule, and the specific way that shape allows hydrogen bonds to lock into an open, spacious lattice rather than a tightly packed cluster when the temperature drops low enough. Change that molecular angle even slightly, and the entire outcome changes. The hexagonal lattice wouldn't form the same way. The density anomaly might not exist at all, and the floating ice cube in your glass right now might simply sink to the bottom like almost everything else in the universe does. So the next time you drop an ice cube into a drink and watch it bob casually on the surface, it's worth remembering that you're witnessing a genuinely rare exception to how matter typically behaves, one traceable all the way down to the precise angle of two tiny hydrogen atoms attached to a single oxygen atom, and one that, in a very real sense, helped make it possible for you to exist at all.